I would like to thank everyone that's attending the webinar today, the webinar series, and we're looking forward to talking with Ben today and Tom, and for the people who's listening to us today, we have Professor Ben Eggleton from the University of Sydney, and Ben has very well established record in his research, and he's holding the position of the director of the University of Sydney Nano Institute, and he's the co-director of the New South Wales Smart Sensing Network. And joining us today, Dr. Tom Hu. He's He's from the University of Sydney as well, and he's one of the research leaders with Dr. Ben team. And he's going to talk to us today about some of his work in using the optical sensor technologies related to measuring air quality. So thank you so much, everyone, today for attending, and thank you, Ben, thank you, Tom, and we're looking forward to your talk.
Thanks, Mona. Thanks for those that are listening. Thanks for that introduction. So Tom and I are both at the University of Sydney, and we've decided to do a bit of a tag team here. We were both independently asked to speak. But because we work very much on the same activity as it relates to air quality, we thought we'd bring these two presentations together. So I'm going to spend the first 20 minutes with a reasonably high-level introduction. I want to talk a little bit about, I'll go to the next slide here, Sydney Nano, because that's an important multidisciplinary initiative at the University of Sydney, and it does connect with some of the agendas that your website says that you're interested in. So I'll talk briefly about that. I'll then segue and introduce the New South Wales Smart Sensing Network and sort of set the scene in terms of how we fit into the ecosystem, how we came about, what the opportunity is locally, then globally, and then talk about how we've structured the program in terms of the thematic areas that are important, and obviously that then sets the scene for one particular project, which is really the focus of what Tom will talk about, which is around smart sensors for measuring air quality, particularly around transport corridors, and I'll let Tom tease out that particular story, and then we'll have some time at the end, I think, for some Q&A, so that should allow plenty of time for questions. So let's go to the next slide. And so I've got various hats on. I've been at the University of Sydney for about 16 years. I was previously at Bell Labs in the US. I'm a professor in the School of Physics, and I led a major photonics program at the University of Sydney for about 15 years. And one of its major successes was that we secured funding from the federal government and from the University of Sydney for a new nanoscience building. That was launched in about 2015-16. We moved in here in about 2015. It was launched, I think, in 2016. And that nanoscience building that was initially a building designed to support physics, photonics, and quantum science in particular, has become, as well as continuing to support those particular research domains, the headquarters for a pan-university multidisciplinary initiative that I'm now director of. And so that spans across all areas of the university's research. Medicine, health is a large part of our agenda, working with Safe Site, cardiovascular, nanomedicine, but engineering, the physical sciences, but we also reach into the social sciences. So let me just sort of talk a little bit about that. I can hear some background noise, so I guess there should be a protocol. I think if you're listening, you probably mute yourself.
Yes. So kindly, please, if anyone has his microphone not on mute, just to put it mute. I think probably they are not hearing us.
That's one of the weaknesses of this approach.
Yeah.
Anyway,
I will message the person. Yeah. Sorry about that.
So just to get very quickly to the point, I've got a slide here that introduces Nano, and I guess given it's Apollo 11 celebratory month, we often like to draw that analogy with that giant leap that was taken just over 50 years ago, deep within to nano science, the nano scale, and of course nano itself is about 60 years old. It was first introduced by Nobel Prize winning physicist in 1959 when he first said there's plenty of room at the bottom. And he imagined for the first time the possibilities that were available in terms of technology if one could assemble devices at the nanoscale. And of course, he didn't imagine that it would also translate into massive applications in medicine, health, energy, communications, this very broad agenda that's captured in those images. So as I said, a lot of what we do is dealing with medicine and health, working in nanomedicine in particular, whether it's using nanoparticles to deliver gene therapy, whether it's developing nanoscale sensors or nanoscale robots even that can manipulate within the body, or if it's understanding nanotoxins, which obviously has a bit of an overlap with the air quality monitoring. So we've got a flagship led from the School of Pharmacy that deals with what's called nanosafety. And importantly, we are headquartered in the City Nanoscience Hub. So this is the building that I alluded to earlier. This was announced in 2009 with a $40 million grant from the federal government, matched by the university with about 50 eventually. Probably all up, it cost about $125 million to build this nanoscience building. So this is behind the School of Physics on Physics Road. The ground floor is all laboratory, clean room space, but importantly, we have about 800 square meters of class 10, class 100 clean room space that allows us to do nanofabrication. Primarily at the moment for solid state devices, there is a conversation about how we might put into some of the new medical buildings that are going up on campus, so-called PC2 clean room space that would allow for more biocompatible nano device research, which I'm hugely enthusiastic about. So that's, I guess, part of the next phase. But you get, I think, from this image here, a sense of the scale of investment that has gone into this infrastructure. Certainly the best in Australia by far in terms of the performance of the building and the infrastructure available, and arguably one of the best in the world. We're helped partly simply by the geophysics of Sydney. So we're built into the side of a hill. We've got Sydney very stable. We're a mile from a railway line. So it's a really exquisite place for a nanoscience building. So very quickly, in terms of our research, it's fair to say that we're still in the early phase of Sydney Nano's strategy. We're rolling out new programs only next week, but in the first phase, we have established what we call the Sydney Nano Grand Challenge project. So these are 6 projects that represent multidisciplinary research programs that address truly grand challenges. So the 6 are listed there: safe by design, sustainable nanotechnology, addresses the grand challenge of understanding nanotoxins in our world. So this is around providing thought leadership, influencing regulatory frameworks, bringing together researchers from chemistry, pharmacy, business, law, to really provide that national leadership. Advanced capture of water from the atmosphere is around the grand challenge of water. Clean water using nano-structured materials to extract water efficiently out of the atmosphere. Nanotechnology for carbon neutral manufacturing, addressing the grand challenge of, carbon neutral manufacturing speaks for itself. Sustainable manufacturing, really at the core, this is a project around catalysis. Unlocking the neural interface, addressing the grand challenge of mental health, disease, through interfaces that are direct with the brain, the neurons. Next generation material discovery, addressing grand challenges in material science, and this is all about utilizing quantum computers and machine learning to design next generation materials. And finally, molecular nanorobotics for healthcare. So this is around unmet needs of surgeons for very precise surgical applications. So these projects are in their infancy, but I would suggest that we're going to see some great things by the end of the year. So let me move to the next slide and sort of set the scene in terms of the sensor technology. So Tom's going to talk about a photonic sensor. So I thought probably worth just pausing and explaining why photonics. So this is the topic that my research group really leads Australia in, and photonics, as suggested by this slide, really draws a parallel with electronics, which is controlling electrons, underpinning computers. Photonics simply deals with controlling and manipulating photons, which are the building blocks of light. Photonics is about as old as the laser itself. So when you think of photonics, you're really thinking about a technology that's enabled by a laser, and in the context of the air quality sensor, it indeed is a laser-enabled particulate monitor. So we talk about photons, it's really an electromagnetic wave described by Maxwell's equation, but as I said, and as summarized on the slide, it's really born with the invention of the laser in the 1960s and the deployment of optical fiber communication systems. Shown on the slide there is just an artist's impression of a chip. So this is the long-term agenda here at Sydney Nano. One of them is to miniaturize these optical systems onto a chip the size of one's thumbnail. So that really allows you to think about potentially incorporating these sensors and other technologies into the smartphone, even onto the body and so forth. So the next slide, photonics plays an enormously important role in all sectors. Clearly, it's the backbone of the internet, plays an important role with microwave communication systems and radar. It is the basis of quantum secure communication systems. And in the context of our smart sensing network, it is the basis for a whole range of important sensing devices. And this is basically because the light field either is scattered off particles in the air, in the case of particulate monitoring, or it's absorbed by chemicals in the air or in our blood. So spectroscopy and the Mie scattering that we rely on here allows us to sense the environment, our health, using optical technology, using photonic technology, using lasers. And of course, as I mentioned in that previous slide, the ability to miniaturize these photonic technologies opens up the opportunity to build these functions into the smartphone to truly empower individuals. So I'll move on to the next slide and sort of segue to what is a really important initiative that we established about 3 years ago. It started as a conversation between myself and my colleague, Justin Gooding, who's a professor at the University of New South Wales in the School of Chemistry, a very preeminent academic, a laureate fellow of the Academy of Science. We both are, in fact. And we had both independently been talking to Professor Mary O'Kane, the chief scientist and engineer, about sensors. And I think it's fair to say that Mary had the view that sensors could address many of the concerns facing her office. Her chief scientist's office had become very busy with, and I'll go to the next slide, with many real-world problems in the environment. For example, black lung disease around the Hunter Valley coal corridor was in the media a lot, not so much recently for various reasons. Her office spent a lot of time writing reports on the so-called coal rail corridor, around transport corridors, and really understanding the impact of the coal industry and more generally the impact of transport corridors and health. There was and there is the ongoing issue around wildlife. We had lots of interesting conversations with experts on koalas. And of course, there's the well-established problem on toxins, PFOS, PFAS in the waterways, particularly around Williamstown. I mean, that's only scratching the surface, really, if you think about some of the sort of broader context for sensors. You know, there's a conversation right now with Sydney Water and the Minister about organising a summit on water, spanning across the Murray-Darling, the drought, the fact that water is leaking out of the pipes, the toxins in the harbour, extracting water, which goes back to the example from Sydney Nano I alluded to earlier. Of course, the more general issue of ageing population, chronic disease, we've got the data explosion, security conditions are changing. So that all sort of set the scene for a conversation about establishing the network. Now I'll go to the next slide, which is slide 11, and it kind of gives you a bit of a global perspective. Not only do the sensors themselves, smart sensors, and I should be clear, when we say smart, sensor, we kind of invoke the notion that we're smarty pants, we're going to build smart sensors, but it's really obviously drawing the idea of the smartphone, the connected network of sensors, and the narrative around sensor fusion, which is the idea of the Internet of Things. If you look at the scale of the business around the world, it's massive. It's taking off right now. It's fair to say that sensors have been around for a long time. When I was a PhD student in the early 90s, student in the office, the lab next door to mine was working for Airbus to develop fiber optic sensors to put in the wings. I mean, that's still an idea that is being developed. I think what has changed is, well, on the one hand, smartphones, the Internet of Things is now available, the cloud. I think there is a maturity in sensing technology and an understanding that it can really bring value to stakeholders, concrete value. In this case, it's the state government that's looking for the value to solve many of the real world problems that cost it a lot of money, and it represents a commercialization opportunity. So our mission not only is to therefore use smart sensors to solve some of those local problems, but because they're global opportunities, it is to translate these sensors into a product to generate, to monetize those smart sensors. And that's probably, it's fair to say, being given a real boost by the new chief scientist and engineer, Professor Hugh Durrant-White, who's, I guess it's fair to say, much more entrepreneurial, much more focused on prosperity, particularly as it relates to commercialization. So the next slide, our vision, very simply, to transform the New South Wales smart sensing ecosystem and advance the prosperity of the state through solutions and opportunities that we create. And we're going to achieve that goal by bringing expertise together from academia, industry and government to position New South Wales as a global leader in smart sensing innovation. So we represent then a consortium. So on slide 13, you can see 8 universities. So we're headquartered at the University of Sydney and UNSW. So we have contract comes through Sydney University, but very much it's a partnership with UNSW. And we then now have these 8 universities. And I think what's missing from this slide, now we've got ANU there, we've got 8 universities, and we're in negotiations with a couple of other universities. So this is quite a consortium of institutions. And in terms of the governance business model, the money from the state government provides the office and employs people like Tom, or co-funds people like Tom as theme leaders. It pays for chief operations officer, administrators, business development, and we rely on a modest payment from the member universities who pay a subscription fee to be a member. And the value, of course, is that they will get is through commission projects that we will bring to them as members. I think we probably expect to reach a steady state next year. I think there are 2 other universities that we expect to join up, and then I think that's probably where we hope to reach a steady state for the time being. So the next slide just talks about the capability map that we've done across the network. So we've got loads of experts sitting in engineering, science departments, health, medicine, transport, data. It's clearly an area of strength in New South Wales and Australia. Whether that's got to do with our particular conditions, I'm not sure. I guess maybe there is something there, but certainly it's a mature narrative in Australia. There's lots of expertise, and the network doesn't propose to go, around those groups. It's very much around promoting that expertise and building that expertise into a coordinated, integrated capability that can then be brought to end users in industry, particularly in New South Wales. So slide 15, we've compartmentalized our program into 6 themes. So this has been based on some business development work that we did, looking at New South Wales financial sort of business perspective, and the scale of the various sectors. But it kind of makes sense as well. We organise our projects and our conversations according to these different themes: built environment. So that's looking at structural integrity, air quality. Although air quality covers a number of different thematic areas, environment and ag tech. There's a lot of smart sensing and ag tech. I've just come from a conversation on campus with one of our, well, with our top researcher looking at sensors that may be used to sense soil moisture in farms, smart sensors in manufacturing, smart warehouses, a lot of data already been used by companies like Amazon, I mean, for good or for bad there. MedTech, huge area. This is an area where Justin Gooding's group has got some real preeminence, but we already know that sensors have been used in healthcare. Resources and energy, that includes autonomous vehicles. And then finally, space and aviation. So that might refer to the Aerotropolis, where there's a lot of good conversations around how sensors can be deployed in a greenfield site there. Smart cities comes up there. Also aviation, there's a big project at the University of Sydney that both Tom and I are involved in, which is dealing with the Royal Australian Air Force and bringing smart sensors to play in a defence context. So just before I hand over to Tom, I thought I'd give you one example of how we operate. So this slide now, slide 16, kind of brings across the entire ecosystem. And so you can see the knowledge demand, which is clearly going to be the departments in the New South Wales Government, OEH, Department of Industry, Sydney Water, utility company, Hunter Water, Meat Livestock, Australia Mining. But we've also got the Air Force, and you can list, you know, hundreds of other end users, if you like, government and industry. You have knowledge supply, which is represented by those 8 universities who are members. They are then either the host institutions, University of Sydney, University of New South Wales, or the universities that pay to be a member. And then you've got commercialisation pathways, vehicles, companies that are involved. So Zeladec is involved in the Sydney Water Project that I'll allude to in the next slide. And some of the usual suspects appear. So I think the last slide I'm going to mention is just one example. It's a great project. This was announced earlier this year. It's a large project with Sydney Water. Sydney Water manages 22,000 kilometres of underground pipes delivering clean drinking water across the Sydney region. And it turns out that they lose between 8 and 10% of the water through cracks in pipes, which is equivalent to the amount of water that the desalination plant creates. This is a global problem. All cities around the world suffer. Some cities have bigger problems than ours. So we talk to other water utilities across Australia, including Melbourne Water, South Australia Water, Hunter Valley Water. Also, we talk to Yorkshire Water in the UK. What we've done here is assembled a coalition of universities and companies that brings together a broad range of expertise and skills to address this grand challenge in water leakage. And these project includes acoustic sensing, LiDAR, drones. We're measuring soil moisture using quantum sensors, and there's a lot of data analytics. So this project's been going for less than 6 months, and we have regular steering committee meetings that I chair with Dharmak Banataj from Sydney Water, who's general manager, and it's a really exciting project. Really exemplifies what our mission is. So I think I'm going to get to the end of my my own presentation. I'm going to hand over to Tom. You've got then a set of information that I guess you can just see when Tom finishes up. We've got Twitter, LinkedIn, website. And Tom, if you're there,
yes,
I'm going to now hand over to you. And I think what I'm supposed to do is stop share.
yes,
And that should allow you to then take over the driving seat. And I'll hang around so when we come to about 20 past, we can have some Q&A. Okay, I'm now pressing stop share.
okay.
Thank you so much, Ben. Thank you.
And then let me just do this. And I should be on here. So Hopefully,
Yeah.
Mona, you'll tell me if something's not working.
No, it's working perfect. Thank you.
Okay, great. Now I'm just gonna,
Right.
there we go. Thanks so much. Thanks so much, Ben, for the lovely introduction. And I'll be taking over, as Ben has said, and thank everyone else for listening in. So I won't go over an introduction of myself, but I'll just continue on from Ben's presentation, saying that this is one case study in particular that we've been working on, which is the development of optical particle counters. We've done both short and long-term tests. And I will say I've got a physics background, so this was a new field for me. And so a lot of this work was done in partnership with the Department of Planning, Industry and Environment, formerly the OEH. And I think they've got a new title now. So I would like to keep that up front and center because a lot of their support has helped us bring us along the way. So the start of, let me just see, all of this work really happened, as Ben mentioned, with Professor Mary O'Kane, who brought up the challenge when she was looking into these transport corridors particularly around rail. And there was a very extensive report that she did, and one of those recommendations was to build a sensor network around rail corridors, focusing on particulate matter. There were others as well, but there was a mention about particulate matter, how far did these particulate matter pollution extend. And what was required to really measure all that was a low-cost sensor, which was able to be measuring real time in a networked environment. And a lot of people have been looking into this, and it's quite a big challenge, and we're also looking into this as well. And it's quite tricky because you can imagine a train would typically go past an area within a minute or two, so you do really need some fast measurements. So we started exploring this around 2 to 3 years ago. And then immediately what we found out was that we were being pulled in two directions from probably what you'll consider to be traditional monitoring, which really focuses on long-term collection, accuracy, and robustness. On the other side, we're being pulled because we're getting pulled along by this new wave of smart IoT devices, which is all about low latency, create lots of data, do machine learning or all sorts of algorithms on top, and work out the data later on. That was already the challenge that we were faced. And then somewhere in the sweet spot we had to be in, which was a network, low cost, and real-time sensor. So then we thought, well, what's on the market? What can we use that's out there right now? And for those who are familiar with the field, probably know a lot of people are working with devices like this. So you can buy these off the shelf. On the left, there's a very small sensor, the plant tower. On the right, there is the dial-off sensor. I'm not sure if you can see my mouse. And these are very good because they're compact, they're low cost, and relatively easy to integrate. But each one has a little bit of a black box type of operation as that we don't really know with these plant towers. We know that it's optically based, but we don't know exactly how it's converting particle counts to more familiar mass measurements of particles. And with the dial-off one, typically with the standard software you get with them, they don't really log at a really fast time scale. So it's a little bit hard to get inside and customize these sensors. So we took a step back because we know a lot of people are working on these sensors. So we took a step back and say, hey, let's create the sensors really from ground up so we truly understand the signal, all the information that's coming from these sensors. Because our strength is in photonics, so we thought we may build it from ground up. So we started prototyping our devices very early on. Here's just a really early picture we had in the lab, comparing it to one of these dial-off sensors. You can see two little black boxes here, which are our custom-made 3D printed proof of concept devices. And then we tested them in the lab against smoke emissions or smoke burns. And we had in time, of course, here, two events that happened. And with the dial-off sensor, which really only logs a minute, every per minute, you might expect a signal which is similar to this. Obviously, the counts go up when the smoke is introduced. And then we really ramped up the electronic speed on our detectors to see, can we really get high resolution of our sensors? And what you see here is a really ramped up temporal resolution of particulates in the lab. And it does get a little bit noisier because you're running it really fast, but you can see some patterns between the two sensors in blue there. And we're trying to see if there's any information at these really fast timescales that you can get that's actually useful. So that was quite nice. The proof of concept was there, so we kept building on. So we moved on from 3D printed devices, and we moved to a little bit more of a prototype device. And there's a little cartoon on the left there that shows you the working principle. It's quite simple or familiar to other technologies out there. So you're looking at essentially a laser beam, which hits particles, and by me scattering, you do get a signal, which is then converted into a voltage using a photodiode. And by looking at those signals carefully, you can understand the size of the particles to some extent. And we built these devices and we test them in chambers inside labs. You can get quite good agreements to other particle counters. We typically use the TSI optical particle counter, mainly because of the convenience of its use. We tested them with more robust methods, which I'll explain later on. So in the lab, we're able to you can just draw a straight line of correlation and get an 85%, which is quite easy. But what we really focused on was what really happens down here is low concentrations. And for those you know, I mean, typically you won't be getting 150 micrograms per cubic meter on an average day in Sydney. You're typically looking more between 0 to maybe 20, and that's quite high. So we want to know, how can these sensors perform at ambient air qualities? So we started testing these, and we were looking at short-term indoor testing, which is a lower level PM. So this is the setup that we had. We had 3 of our little sensors made up, and we compared that to the TSI optical particle sizer, and we moved them around just within our labs for just a quick laboratory test. So the 3 rooms that we went through, one was in the building Sydney Nano Lab, which Ben was just speaking from, which really boasts a clean environment because of the nature of the work they do. And then we moved the sensors over to another room, which was in the School of Physics, but it wasn't a working environment. It was inside the compressed air chamber. You basically don't work in there, but it was controlling of the compressed air to the labs. So it's a very noisy, quite dusty environment. And then we went to a standard lab, which was a few doors down from the one above, which is a standard, typical working environment. It was connected to that pump room, however. So we thought it'd be a really good test to see, how our sensors vary at these levels. And this is first the results of the PM, I should mention PM 2.5 in these labs. And this is measured by the TSI optical particle sizer across the 3 labs. So as you can see in the first 30 minutes there, we were inside the clean room or the nano building where the particle counts are extremely low. I think you're looking at an average of less than 1 microgram per cubic meter there. As we move to the pump room, you can see the level goes up, and it's also quite a noisy environment, and you see a lot of these peaks inside. And that actually corresponds to the timing of the pump filters inside the lab, which actually exhaust a huge amount of air every 2 minutes. And if you actually zoom into this data, you can see quite regular peaks of particulates every 2 minutes. So it was able to pick up that. And then in the third lab, you can see that noise is no longer present, but the general level is about the same. So we thought this was quite a good testing chamber, testing setup. So then that's using the off-the-shelf sensor. We're looking at how did our sensors do, the low-cost, really small, compact sensors, and these are the results shown here. So what you see here is 3 plots. Each one of those is comparing it to the previous plot, with the black line there showing you the sensor reading from our sensors, and the red line showing you what we took as the ground truth. And I'll just mention maybe the cost of components for these sensors here was typically around the $100 to $200 mark. So you can see that our sensor does pick up most of those features throughout the 3 labs, and also those small spikes within that pump room. And it does have a little bit more noise on it. We are measuring every second. We're not doing any averaging or anything. So what you see there is really the raw data. But what you see is when you compare that to the more expensive sensors, we are getting quite good agreements, roughly averaging about 80, 83 or 4% across those 3 labs. So this was quite good for us. We were thinking, yes, this is on the right track. We've got some local sensors which are agreeing quite well. And we decided to upgrade the sensors a little bit more. So this is what they look like now. So we've gone to, I would say, maybe version 3 or 4. And we've upgraded the looks of the sensor. So that's the sensor down there. It's got the inlet on one side and the exhaust on the other side. It's got a single push button operation, and some brilliant engineers have really helped us link this data that comes out of these to wirelessly communicate online. So what you see there on the back there is a dashboard at a website called UbiDots. And one of these sensors connects via 3G, and essentially it takes in all sorts of data and it will just push them up through the 3G network online to see the data live. We've also turned on a couple of other off-the-shelf sensors as well. As you can see there, there's humidity, temperature, pressure, and also a little bit of VOCs, although they're not quite sure about how accurately those ones perform, but they're really off-the-shelf sensors that you can just easily integrate into sensors. And that's where it stands currently at the moment. And it's quite nice to see all the data live when you're not on the field. And this is just another quick test again. This is over maybe a day and a half measurement indoors as well. And we're getting quite good agreements between our sensor and the standard TSI particle size. So we're in a pretty satisfied situation at this point. But obviously, I think those people who are listening probably already know that it's quite easy to get sensors to agree on a short-term scale, and also especially when you're doing those indoors as well. So then we need to check just some long-term measurements and even also compare them across more standard gravimetric measurements as well. So then this is where we were doing the work in partnership with the Office of Environment and Heritage, and we've taken these sensors outdoors. This is over at the Chullora site, and we're doing really long-term tests now comparing against more standard measurements. And a lot of work went into making sure that the sensors can be self-powered, that we don't need to go out to the field and tinker with them as they're running. I've written data security there, but it's really about how to make sure we don't have any missing data, making sure that the data communications are solid, timestamping, and then obviously the last most difficult one was probably making sure that the sensors are environmentally robust. So you're looking at all different kinds of weathers, and from rainy days to foggy days to extreme heat as well. So this is the work we did over the summer of 2018 to early 2019. And here is the results that we measured for, this is the 1 month measurement. We did do it for 3 months, but I'm just showing you 1 month of it. So these are two of our sensors in red and another one in blue there. And this is showing you particle counts. I think we were measuring every minute and uploading the data every hour over essentially a month here. And what you can see there is you can see sharp events in particle counts in time. I'll come to what these are in a moment. But what you can see is there's quite good visual agreement between the red and the blue curves there. They've just been shifted for clarity. But with inter-sensor comparison was showing a good agreement for 91%. And we didn't have any data loss, so we didn't have to go onto the site to repair any sensors. So the question is, we co-located these sensors with the Office of Environment and Heritage with more gravimetric sensors, and how did those compare? And the unfortunate answer was they did not compare very well. There was a reason for this, and I'll get to this. So what you're seeing here is the measurements done by the band using these more gravimetric methods. So they're essentially methods where you have a filter and you're collecting particles through a controlled air inlet, and then you're weighing that mass over time. And this is showing you the results at the same time as our measurements for both PM 2.5 and in the middle panel, PM 10 measurements, and then on the bottom out one. So I don't think no matter how many times you squint your eyes, you can't see a good agreement between these curves. So we thought, okay, it's probably time to go back to the drawing board and find out what's going wrong. And what was interesting though was before we did that, we actually compared it to a nephelometer device that was also set up by the Office of Environment and Heritage. And if you compare it to those data, this is what it looks like. So these are the same results in red and blue, but now you're comparing against nephelometer, which is an optical measurement of particulate matter, and that's in the green curve at the top. And you can see there's actually quite good agreement across these. And so we were a little bit thinking, okay, so what's going on here? And I'll come to why the optical methods and the gravimetric methods don't agree very well, but I'll just go to what these peaks are coming from. So okay, so we've got a rather more sophisticated nephelometer sensor, which is reading a certain value, and we're also reading these values too. So then we started looking at other data. First, can we explain what these spikes are coming from? Here's just a zoom up of just one of those sensors. And we particularly noticed that these peaks correlated very strongly with a particular time and a particular wind direction as well. So all of these peaks seem to be happening around, I think it was around midnight to maybe sometime between 2 a.m. and happening all at the same time. And then if you compare the wind vector at the time, I'm not sure if you can see from here, but I'll just highlight it. You can see that a lot of the peaks do indeed happen when the wind is blowing a particular direction. And in this case, it's this north-northeast type of direction. So then we asked, well, first of all, we consulted with the Office of OEH people as well, who are very familiar with the local environment. And we were actually able to identify that these were actually being emitted from a particular industrial activity, which was southwest of the sensor location. So when you have those two conditions meet, which was the wind was blowing from a particular direction and the time was right, you do get these spikes from emissions. And but I will say they're not alarmingly high levels, so I'm not saying this is anything drastic, but it was good that you can kind of look at other data sets and identify where these peaks are indeed coming from. So I think the more important question is why the optical methods that we have and also the OEH had were not matching very well with the gravimetric methods. I can at least speak for our sensors. I would say it's because we are still just counting particles, and that's what an optical method does, and we're not weighing the particles per se. So in order to do so, you do need quite a strong calibration to convert from basically counts to mass. And that requires knowing a lot about the size, shape, and also the density of the particles, which is a part that I think a lot of sensors out there don't do. And I think a lot of people who work with low-cost sensors probably struggle because of mainly this cause. And without going too much into the theory of it, we do know if you want to convert from particle count to mass, you do need to sum up all the particles. You have to understand their volume, the density, and then the amount of air that you've sampled, and sort of formula here, but I'll just simplify it. So, of course, you have to count the particles, you have to measure the size of them, and assume a density, and then also the sampled air, which should be quite a simple one. There's a lot of assumptions you have to make, and that really leads to a weakness is that optical particle counters are sensitive to size variations when converting to mass. Because as soon as you have one 10 micron particle versus a 10 nanometer particle, the volume goes as R cubed, so the amount of volume difference there is ridiculously big. Whereas an optical particle counter will still count them as one and one the same. So I think, I'm not saying it's impossible, but you just got to be really careful when you do these conversions and make sure you have the calibrations set really accurately. And that's what we're working on right now. So at the moment, we're building more setups to be able to produce a certain size range of particles and do really accurate calibrations. One thing we realized is that our recent test showed that when we exposed our sensors to 2 micron diameter particles, we were completely saturating the readings. So we'll still count them, but it'll saturate the sensors in terms of the voltage. So we're actually believing we're looking really small particles, probably below PM2, as we would say. So that's where I would like to go from here, is really get a lab where we can generate aerosols very accurately and see how far down we can see, even down to typically hundreds of nanometers. And I think with Ben's nano lab next door, it's a really good place to be in to be testing these sensors. So that's where it brings us to. And then I think moving onwards though, so we do have a sensor that does agree with nephelometric readings. And so we are pushing on ahead with getting our sensors out there and doing more tests. So we do have fast, low-cost particle sensors. Currently, so we've built the sensors ground up. We know that there are limits when we're going to gravimetric methods. But in future, what we want to do is, and we've actually already started, is to get a sensor mesh network or a sensor star network to happen. We've got some bright engineers who are and updating our communications by using LoRaWAN communications, so we can have multiple sensors all communicating to the one device, so that we don't need to have essentially SIM cards for every sensor. So this is happening, and this is quite exciting, and we want to be able to do this to potentially measure the transport corridors that I mentioned very early on. So I'm not sure how we're doing for time, but I think that brings me to the end of mine. I just wanted to finish with some acknowledgement of the people that have made this work possible. The Egerton Laboratory, which is Ben's group, particular engineer there, I'd like to shout out to Luke Mackay, who has helped me develop a lot of these sensors. In the New South Smart Sensing Network, we've also had some very good advice from engineers Samuel. And then I'd also like to acknowledge the partnership with the Department of Planning, Industry and Environment. Matt Riley and Yvonne Squoggy there really initiated this work. And the people on the ground, Ruby, John and Gunnar, are really patient with me and teaching me about how to do monitoring measurements from monitoring measurements 101. So big thanks to everyone on this page. And that brings me to the end of my session presentation. Thanks everyone else for listening, and I think we're believe we'll be going to question time.
Thank you so much, Tom, and thank you so much, Ben, for the interesting talk. And I think everyone in CAR was really looking forward to hear more about the work that have been done in New South Wales Smart Sensor Network. So thank you so much for your time. I really appreciate it. And I'm going to open now the platform. If anyone has a question, we can go ahead with the questions. I will check if thanks so much.
It's Jeff here.
Hello, hi Jeff. Sorry, we can't really hear you. Well, can you put the volume a little bit up?
How's that? Is that better?
Yes, that's perfect. Thank you.
Okay. So, am I in a line or is it me?
Yes, you are. You're talking. Yes.
Look, thanks for that. It's really exciting what you're looking at. I was just wondering the last speaker, from a health perspective. We're very focused on mass measures because that's where the science is in relation to health effects. And so, and from a mass perspective, we've seen sensors for many years come with lots of big promises around being good proxies for mass measures, and that the results have been mixed. So, just if I could ask the last presenter, do you think it's possible to get good, robust measures of mass from a particle sensor in a particular size range, even?
Yep. So I'll jump in. Yeah, and I do think the simple answer is yes. I do think there is, and some of the sensors optical sensors that we actually. So I guess the question. The mass measurements done with the traditional sensors, I believe, are quite accurate. Now, do you mean in terms of low cost optical sensors? If that's the case, then I would say yes, it is possible, certainly possible, if you have a good understanding about the size and density of the particles, then you can convert that to a mass. There's a nice conversion that you can do. At least from the people who I've spoken to, you can get an idea about size. If you assume a particle size, you can do it. But I've heard a lot of monitoring people have struggled to make that accurate conversion because different environments do have different compositions of particles. So you have to make certain assumptions about correction factors depending on what kind of area you're in, whether it be on the seashore where you've got quite a high number of salt particles and things. So you will need to have some idea about composition when you want to make a really accurate conversion to mass.
It just seemed like you needed to have that information needed almost to be in real time as well.
That's correct, and that's the difficult part. And I think Ben would agree that's a bit of a holy grail about counting the particles is important because you're getting a high time resolution, but you also need to, in real time, find out, well, what kind of particle was that? And I think you could potentially look into other methods, or, we've got a really simple particle counter, but if you start using spectral analysis, for instance, you may be able to get some idea about what kind of particle it was. And that would be quite an interesting sensor to develop.
Great.
I have a question. Thank you so much, Tommy. I have a question I've been sent, and it's from Gerald. He's saying, thanks for the insightful presentation. As I'm sure you are aware, there is a lot of issues around bringing innovation to the market. How do you go about education big corporations on sensing technology so that they invest on this matter? How is your go-to-market approach? I think this is for you, Ben.
Yeah, I mean, that's a big open-ended question. How do you go about educating big corporations on sensing technology? I'm not sure if we have been educating big corporations. I mean, we've certainly been promoting the smart sensing agenda. We've been very active in speaking across the sector when there are opportunities to promote this narrative, and we have certainly looked at various commercialization pathways for this particular sensor. I mean, it's worth noting, the Smart Sensing Network is quite a broad portfolio of sensor technologies, some of which have already been commercialized. And there's quite a robust sensing market, as I indicated. The local context, we've had some struggles, looked at joint ventures, partnering with companies. I think the current thinking, if I can say, Tom, with respect to the air quality sensor would be a more organic sort of spin-off to incubate that technology, which is what we're doing at the moment. It's about finding the customer and the customer who's prepared to put some money on the table, and that's where we're at the moment. We've got a bit of tension there between, on the one hand, working with the end users of the state government to help them solve some critical issues around transport corridors, and then finding that customer, that market pull that allows us to monetize this technology. And I guess, it's fair to say we haven't cracked that one yet. Tom, what do you think? How would you say it differently, or?
No, I wouldn't say differently. I would pretty much say the same. The organic growth is what we've been thinking about, and then finding out, how to grow the technology through a startup would be interesting. But the only thing I would add is I'm on mute. The only thing I would add is, what was I going to say? Lost my train of thought.
Well, let me step in, Tom, while you're getting your train of thought. I mean, part of the challenge is there's not a lot of money in air quality sensors as such. It's not an area where you're going to crack a huge market. My personal view is, but at the same time, there are plenty of companies out there that are productizing, monetizing sensors, and it is addressing a hugely important issue. Now, there is sort of the narrative in Australia as we all look outside and we see this beautiful blue sky. People think that we are living in this very healthy environment, which in general is true relative to many parts of the world. So the market's global. The Chinese companies have been selling these air quality particulate sensors for several years, and you can buy them off eBay. How much, Tom? What do they cost?
It could be ranging from $10 to
yeah. So and they print thousands and thousands of them. What we've tried to do is build a more sophisticated, advanced sensor built on a lot of smarts that really allows us to understand the engineering physics constraints and bring a lot of value to some of these local problems. I'm not sure if that's enough to answer Geraldine's question. Happy to take that further. We've only got about 6 minutes. Happy to have a conversation offline if that is interesting.
I've got a question, if I could ask it.
Yep, go ahead.
It's Christine Cower here. Thanks, thanks Tom and Ben for the talk. That was really great to know where you're up to. I'm just wondering, given what Tom, what you said about the need for calibrate, it's almost like a recalibration of the data that you're getting, and that's, from what I understand, and please correct me if I'm wrong, and that is reliant on knowing knowing the composition of the particles, and we know that that's not easy to get that data. I mean, I know that OEH and ANSTO have a good idea of what the particle sources are across Sydney, and the composition is, but obviously, like you said, that can vary from day to day. And then the other thing that you also said was that the sensors are being saturated by PM, which is less than 2 microns. I'm just wondering, given that, have you thought about ultrafines at all, or trying to convert the sensors to detecting black carbon, for instance? And I know that PM 2.5 is really what is driving a lot of the health guidelines, but there is a move to doing a bit more ultrafine particle measurement, and also hopefully black carbon, even though there's no health guidelines for them. I mean, is that a level of sophistication that's you know, way beyond where your sensor is at the moment, or do you think that could be somewhere where you could go? Because I ask that because the current devices cost about 10 grand each, so that's, I mean, it's certainly lower cost than your sophisticated, but it's certainly not that low cost from a public health study point of view.
Yep. So maybe I'll start with unpacking maybe I had said it wrong, but so we were saturated because the particles larger than 2 microns. So we were actually looking at a smaller size range. So just maybe I did say it wrong, so I'll just correct that. So yeah, so we are looking in a size range that we believe is 2 micron and below, and we haven't quite got the expertise to build 50 nanometer particles. And that's what the lower limit of our sensors are, although we are doing some collaborative experiments with a geosciences group who is doing this. So we definitely are interested in the ultrafines, and I think that's where the optical counters really start to show a lot of advantages, because when you're trying to measure the mass of ultrafine particles, that's really difficult. I mean, they barely don't weigh anything at all. So the accuracy in terms of mass measurements won't be as good as, for instance, doing counts. And there's pros and cons of each side, but I think in the ultrafine, the optical methods will start showing its advantages. When it comes...
sorry, I suppose that's why I asked, because currently the devices count the ultrafine particles rather than measure any mass. So, yes. Which sounds like that's where your sensors, that's what they're good at doing. Yes,
that's right. Yeah. And it's this kind of balance between, and there are the ones that are on the market now are quite sophisticated in terms that it has to first dry out the air, swell the particles up in a controlled way using moisture, and then measure that as they travel along. You know, we don't want to just reinvent that wheel as well. So we're just going to see with the optimized optical performance we have now, how low is it going, and how much more can we go by, for instance, using some of the photonics work we've done here, change the laser frequency, use more advanced detectors to see about new ways of measuring the ultrafines. And that does also lead to, when you come to the black carbon measurements, and did you mention there were 10K each, the ones out there? I mean, they're usually based on some kind of deposition on a film, and then you're doing essentially spectroscopy, or measuring basically different absorptions of visible light. And you can make an assumption about that. Potentially an avenue we can go down as well. I think, yeah, those methods are really like it's not really a single counting method. It'd be interesting to think what you could do with a single counting method with multiple wavelengths, and that will tell you whether it's black carbon or not as in real time. I don't think it's impossible, but it will involve a pretty sophisticated sensor as well. And we've always been looking, moving beyond the standard particle counter. So down the avenue will be something we will be exploring.
Thank you so much, Tom, and thank you, Christian. We have 1 minute left, and there's a question has been posted on the group chat. So, do you think, Ben, from your experience, from the collaboration with health researchers, do you think we can answer that question?
I'm just wondering, is it based on gravimetric methods? Is there emerging research concerned about particle counts? Use standards.
It's Craig here. I thought it might be something that Jeff or some of the other researchers into particle counts could, particle impacts could comment on, whether absolute counts are going to become more important and useful in time.
I don't know the answer to that. I mean, it's where we have in the Sydney Nano context this nano safety agenda led by Wojtek Kronowski and the School of Pharmacy, and it's not quite in that. But yeah, I don't know the answer to that one. That's an interesting question.
Maybe that will be a chance for us to find another interesting seminar to think about it from both health perspective and nanoscience perspective in the upcoming series.
Look, there's been a lot of work, it's Jeff here, there's been a lot of work done in this in relation to health. And while various aspects of particulate measurement have been assessed in great detail, it's remarkable how robust the mass measure of particle is remaining as a focus for health studies.
Thanks, Jeff.
Thanks, Jeff.
Interesting. Yep.
Yeah.
It's Martin here. Can I just ask one quick question? Tom, I think what you presented is really good. We've been doing a lot of work with plantails. Fabian Resin and the work that she's been doing with STEM, small things.
Yeah.
And I reckon the real value that we would see in replacing the plantail with an instrument designed from the bottom up, even if it only had the capability of the plantail, is transparency in terms of how it's been put together and the factors that are used to convert from scattering to mass or number. And we've seen that with a couple of US EPA monitors where they've written papers on actually how it's done. And so even getting to that point where it's totally clear, I think would be of great advantage. And to finish, if you could then go beyond that to have tunable lasers, where you can then track down through the size distribution via the scattering, that might be a nice way to take it forward.
Interesting, yeah. Thanks for that comment, because definitely agree, because we also had the plantail very upfront, and it was very commonly used, and we went down the different route of wanting to know like every electrical component. We wanted to understand everything that was happening, because we didn't want to be in a situation where we produce a copious amount of data and a little bit unsure about what's happening inside the box. So we did take a longer path. We could have strapped a bunch of plantails together, but we thought the value was in building these ground up.
Yeah, nice concept.
I would like to thank you so much. Thank you, Ben. Thank you, Tom. Thank you for everyone who've been listening today. It was a very interesting talk, and we really appreciate your time and all your insights you've shared with us today. And we're looking forward for more collaboration between CAR and the New South Wales Smart Sensing Network. And thank you, everyone. It was a pleasure.
Great to talk to you. And I guess you can email Tom or I, and come and visit us at Sydney Nano. Happy to show you around.
Yes, that would be lovely. Thank you so much. We're going to do that.
Okay.
Thank you so much, Ben. Thank you. Thank you, Tom.
Bye-bye.
Bye-bye.